Morning everyone. So for the last 2 days here, we've been looking at two different functionalities. One is alcohol functionalities. They have a special OH group. The other family we talked about were an aromatic family. They're based off of benzene. Let me give you a quick warm-up question here. See if you can name some of these diagrams, and if given a word name, see if you can draw the picture. So let's plop down a few other carbons here. Let's give an OH, Cl, F. Okay. We're going to do our aromatic family. Let's do that. Okay. And let's do one more. We'll have 2,5-diiodo 3-propyl cyclohexane 1O. Right. So as usual, I encourage you just to pause the video, try it out for yourself, and then you can check it work with me. Alright, so going over this here, we're going to first find the longest carbon chain. I do very often throw on chlorines. Sometimes people just start confusing. Well, chlorine, even though it does start with C, it's actually not part of the carbon chain. The carbon chain here is going to be just 5 carbons long here. We have fluorine and chlorine. Normally, would actually count it left to right because then it would be 2,2,4. But remember, the alcohol group here ends up taking priority. It's more special to the molecule, making us actually count it right to left. So just based on the alphabetizing there, the C for chloral comes first. So 4 with the chloral. We have a 4 with the fluoral. Okay, those are the two different branches there. We know we're going to be a pentane, but we have an OH at position number 2. Remember, you either put the 2 in front, so it could be 2-pentanol, or it could be pentane 2-ol. That 2 just represents that the alcohol, the hydroxyl group here, covalently bonded, is actually off of position number 2. Okay, so you'll recognize the alcohol functionality here with the OL. I see that a little bit here with the ending here. That's going to be part of an alcohol. Before we get to that, let's look at this molecule here. They've given us a skeletal diagram. That's all they're going to show you. If you need to, you can plop down the carbons as you need. Okay. All right. Our parent is just going to be this benzene ring. Good. It has those double bond, single bond, double conjugation. So we know the parent is going to be benzene. Benzene should have had just 6 attachments to hydrogen. There's 2 places, though. On the one side, I've attached on a carbon alkyl branch. The other one is going to be a 2-carbon ethyl branch. So let's just alphabetize those there. We have our benzene as our parent name. That's going to be the very last word. We have ethyl and methyl. This one, it really didn't matter which you called 1 or 4. So maybe I put 1 at the ethyl, just for the alphabetizing there. 1 for the ethyl. And I have 4 for the methyl. All right. You could totally have 4 ethyl, 1 methyl. Those, even though it is a slightly different name, that's just the numbers are still as small as you can get them, but both of them are fine. And we talked about here specifically for benzenes with 2 substituents here, you could call this either ortho if it's 1,2, meta if it's 1,3. In this case here, because we're directly across from each other, sometimes they can summarize this part here as the word para. Okay, so if you see para, just means across from each other. If you were thinking after yesterday's lesson, how come I can't be 1,5? Okay, well, let's try it here. If I were a benzene, let's sort of count around here. 1, 2, 3, 4, 5, 6 going down this way. If I try to be, let's say 1,5, how come I don't have a special name for that? If we are only 2 substituents and we're keeping the numbers tiny, a 1,5 would actually be the same as a 1,3 because then I would start counting 1, 2, 3 instead. Similarly, why can't I be a 1,6? Well, that would just be a 1,2 instead. So that's why we just needed the 1,2, 1,3, 1,4. All of them have very specific behaviors as well. In this case here, para, because they're directly across from each other. Okay. All right, this last one here, usually I like starting at the really end of the name. So we have a ring of 6 carbons. So let's just draw 6 carbons here. Remember, we're not a benzene unless we have those double, single, double alternating. This one here is not benzene, so I don't want to add those double bonds. At position 1, we have OL. So OL tells you it's an OH ending. So let's call it 1, 2, 3, 4. Now this molecule here is twisting and rotating in space here. Just for simplicity, as I'm listing it, I'm going to call the top carbon here number 1. let's put on an OH functionality, single bond O, single bond H. That puts me in the alcohol. At 2, 5, there are 2 iota groups somewhere in the picture. Again, a very common mistake I see people do is they end up going, okay, at position 2, that's an I and an I. Okay. Well, 2 problems with that. First thing, when I have an I functionality here, it shouldn't be holding anything else. Okay. I's are not like carbon that can sort of indefinitely bond to itself here. Yes, the diiota tells you there's 2 iodines somewhere in the picture. Only one of them is on 2, one of them is on 5. So I put 1 on 2 there, one of them on 5. And then we have our propyl functionality. Our propyl is going to be a 3-carbon chain, happens to be at spot number 3. So we just plop the 3 carbons that way there. And because these are single bonds here, they can twist no problem. I could just summarize it as C3H7 if I like. I can zigzag it downwards. It doesn't really matter. Okay. Now looking at the branches, I'm definitely going to be 1, 2, 3, and 5. This time here, because the OH does take priority, this has to be position 1. Even though number-wise, counting at 1, 2, 3, 4, 5 would be similarly as 1, 2, 3, 5, the numbers are as small as possible, that would have my hydroxyl group here at a number that's bigger than it needed to be. Okay, so that's why we preserve this naming here. There's the name for that molecule. Lots of information just sort of stored up in that one word name there. Okay. Today we're going to introduce one other functionality here. This functionality, just like our alcohols and aromatic families, you do need to know how to name these directly. As we skip over to tomorrow's lesson, we're just going to survey over 5 or 6 other functionalities. I'll give you a little bit of hints about how they're named, but those ones there, we're just need to label, oh, you have functionality number 1, oh, you have an alcohol, oh, you have an aromatic, oh, you have an ester and whatnot. So these ones you don't need to name in as much detail. Okay. So for today, new functionality here, we'll call this an ester. Okay. Slightly different spelling if you have a friend called Esther. Okay. So an ester functionality here, esters, they contain the group here. Usually we shorthand it COO something. Okay. And just to emphasize that a little bit better here, this COO, if you see that condensed structure, that's sort of shorthand, it stands for carbon. The one oxygen is double bonded. The other oxygen is single bonded. Okay. So COO is representative of this grouping here. Any molecules that have this grouping are referred to as the ester or ester functionality. Okay. Now, as we survey over a few different other functionalities here, this is one of 2 special groupings here because we're very used to, well, organic molecules, they're supposed to have a carbon backbone. They're supposed to have sort of carbons all linked up in a chain, and we try to find the longest carbon parent. For this one here, you'll notice, sure, I can have a long chain over here. Sure, I can have a long chain over here. And ester functionality is something that comes in between a chain. It doesn't need to be smack in the middle. It can even be just 1 carbon inside, okay? But this is one of those functionalities here that actually come in between the chain. And basically, the way IUPAC divides the name of it, they know this is an ester. They're going to change the ending. They're going to make the ending actually O8, O-A-T-E, as we'll see. But because this sort of comes in between a chain, they sort of decided, okay, we're going to just choose one of these sides here to be the parent, one of these sides here to be the branch. They've decided that the carbon side of the ester, however long it is, it doesn't even need to be the longest side, the carbon side is always going to be the parent. This is going to be the last part of the name. Okay, this part here, the parent does not always have the most carbons. We'll see a few examples of this, okay? But let's just decide the carbon side of this molecule here is going to be the parent. That leaves the other side here as our branch. Okay. So the branches always come before the parent. Usually I would need a position for the branch, but I know in this case here the branch has to be off this oxygen side, okay? So the branch here is going to end off with YL, right? It's an alkyl branch, it's a carbon branch. So they've just decided that regardless of which side is longer or shorter, the carbon side of the ester is always going to be the parent side. In fact, in organic chemistry, very often, again, the special part is the ester functionality. It behaves in certain ways. Okay, esters also are fairly smelly. Okay, but to indicate the remainder of the chain, they might actually put on what's called an R group. Okay. Now, if you look on your periodic table, you're not going to find the element R, okay? The R just stands for sort of the remaining of the chain, okay? So this is the rest, the remainder of the chain, okay? So that means this branch here, doesn't matter how long it is, the branch is going to be on the oxygen side. That's going to be another R group. Now, because these R groups might accidentally be thought of as the same, sometimes they might say R prime, R double prime, or whatever, just to indicate, well, this is the rest of the molecule. I don't necessarily care how many carbons are attached on either side, which one's longer or shorter, because I've already decided the carbon side is going to be the parent. Okay. So let me just sort of draft out a little bit of the naming scheme here. Okay. Sure, esters later on could also be substituted and branched with halides, things like that, but this is probably hard enough, just remembering which side is the branch, which side is the parent. So what we're going to do, we're going to count how many carbons in R prime. Okay, so that's the branch side. We're going to change the ending to YL there. Okay. Then we're going to count how many carbons. Okay. Remember this ester functionality here comes in between the chain. Count how many carbons are in the R. That's just going to be the parent. Doesn't matter if it's longer. We can even have a really long oxygen side, long branch side. Still, the carbon side was decided to be the parent. And then all we're going to do is our general formula is going to be the branch comes first. We're going to change the ending to YL. We're going to have the parent come afterwards. Remember, the parent is always the ending of the name. And then we're going to change the ending here to OATE. Okay, so something 08. Okay, so that actually distinguished for me that we are in the ester functionality. Okay, so let's try out an example or two here. Usually I like just sketching the ester functionality first, because I know if I'm in this family here, I better have the COO grouping. Just to indicate to you, well, no, it's not always going to be the carbon side that's the long side. Let's say this only has one extra carbon. Let's plop on a couple other carbons. Okay, I can even sub on all the hydrogens. They don't affect the name. Okay, but if you're just sort of sketching, well, what else is attached to this molecule? We imagine the rest of it is saturated. In the Lewis diagram here, it is understood that these O's here actually have lone pairs. Okay, so they're not actually holding anything else. But for our sake here, we're just going to say, well, this grouping is a very special grouping. Okay, that grouping there comes in between the chain. It has a carbon side of the molecule. This side is going to be decided to be the parent. And this side here is going to be decided as the branch. Okay. Now you might say to me, well, wait a second. How come the branch has 3 carbons? That's longer than the side here. But that's fine. IUPAC has decided the carbon side is always going to be the parent. Okay. And for the parent, because the ester group here has a carbon, the parent is going to end up including that carbon there. Okay. So as we're naming this here, if I had a 3-carbon branch branching off of something, this is on the oxygen side, this is going to be called a propyl branch. Right. Sorry, I actually shouldn't be highlighting the H there. Right. The parent is just from the carbon part, so 3 carbons. So that's going to be a propyl, okay, or propane. We change the ending to YL. The parent, again, because it does include the carbon in that ester functionality here, the parent actually has 2 carbons, okay? So you notice it's not just, oh, don't just count what's in the R chain, actually include what that C is. So we're just going to count that there. We have 1, 2 there. It would have been propyl ethane, okay? But again, to tell me that we're in the ester functionality, we're going to change this ending here to propyl ethanoate, okay? So all you need to really sort of remember for yourself, no matter how long it is, the carbon side is the parent. The oxygen side is going to be the branch. It's going to be the YL ending. What if I swap these around? Okay. What if I had, again, same ester functionality. What if I had the 2 carbons on the one side and I had the total of 3 carbons on this side here? Okay. Again, you can sort of saturate the rest with hydrogens. Understood that there's H's on the ends of all these. Okay. First thing that I would do, again, you'd say, you have the ester functionality. You have that COO functionality, okay? The carbon side has been decided to be the parent. This time, the parent is the longer side, so be it, okay? The parent's going to be the N. This time it's going to be propane with the ending 08. The ethyl group that I put on, oh, this is on the oxygen side. This ends in YL. This is going to be the branch. This comes first. This is actually now going to be ethyl propanoate, okay? Both of those are esters. Both of those have a COO functionality. Hey, they have a different name, So for all intents and purposes, they're different molecules. Okay. Again, what's the relationship between these molecules here? They're actually going to have exactly the same molecular formula, the same number of carbons, oxygens, hydrogens, and all that. But because things are bonded differently here, to interconvert one into the other here, I actually need to physically break some bonds, do some reactions. These are actually structural isomers of each other. So if I had asked you, oh, draw all the structural isomers, if I had this molecule here where I had the ester functionality, I would need to start considering where are all the other places, how could I lengthen the chain on one side and shorten it on the other side here, what are all the possible ways that this ester could be built up. Okay? But those are structural isomers, those are different molecules. Okay? So that's pretty much it for esters. Okay, let me let you practice some here. Sometimes people start getting confused as I start going the opposite way. So let's go. Let's do this. Okay, longer of an ester there. I'll even do one sort of kinked strangely. 2, 3, 4, 5. To make it a little bit different. Okay. So 2 last esters for us just to finish off here. Remember, most of these are single bonds. Most of these are sort of rotating and sort of twisting in space. The first thing you want to do is you want to recognize the fact, what functionality do I have? This functionality here is going to be shorthanded COO. That puts me in the ester functionality. So that means I just need to count how many are on the branch side, how many are on the parent side, no matter which side is longer. Okay. Now, because I'm sort of on the other side of the molecule, the oxygen side, the branch side, is actually this side here. Okay. So this is going to be called a butyl, right? But for 4. Okay. On the other side here, I also, the carbon side here, including the carbon in the ester. Okay. This one here also has 4. So we're actually going to call this name here butanoate. It's possible that both are actually the same length. Okay. But nonetheless, the YL is the oxygen side, the branches of the oxygen side. The parent side is always the C side. Okay. What about the one at the bottom here? This is now really kinked really oddly. Again, if it helps, just plop down the carbons that are on the different corners. Okay. We know our functionality here is going to be the ester grouping. It's the COO part. The oxygen side is going to be the branch. So the branch in our case here has 1, 2, 3, 4, 5. So this part here is going to be called a pentyl. And then the parent side, this time it was actually longer, counting the carbon in that COO grouping. I have 1, 2, 3, 4, 5, 6, 7. Okay, so that's going to be hept. It would have been a heptane, but now we're going to change the ending. Pentyl heptanoate. Okay. So that's how you end up naming esters. Again, your worksheet will have a little bit more practice with that there. Just remember the O side, regardless of how many carbons are attached to it here, that's always the branch, that's always a YL ending on the carbon side, including the C in that COO functionality. That's going to be the parent side, change the ending to OATE. Okay. It is totally possible that there will be branches later on, oh, let's attach an iodine and substitute and whatnot, but usually the questions they ask are just trying to remember which side is branch and which side is the parent side. Okay? If you have any questions, just let me know. Thanks, guys.